right, well, we're not going to let a snow day hurt our progress, so making this little video for you so we can try to keep up with the material. So I want you to listen to this video, and then when we get back in class on Thursday, we're going to spend at least the first portion of the class sort of going through questions and doing some problems to see how well you understand it. So, like I said, Chapter 25 sort of laid out some basic information for us so that we could start to look at circuits. So it helped us understand like the idea of a resistor, introduced Ohm's law to us. Also, what does current mean? So now what we're going to do in this chapter is we're going to start to look at real circuits. We're going to see what they look like when they have a lot of different resistors in. Those resistors might be connected in series or parallel, and we're going to take a look at that. And then also, if we have a situation where it doesn't seem like we could break down a circuit into simple resistors in series and parallel, often a situation where the circuit has more than one battery, we're also going to learn how to do that. And then finally, we won't talk about it in this video, but we will be looking at what we call RC circuits. And those are circuits that have a resistor and a capacitor in. So when we're talking about circuits, in this class, we're going to confine ourselves to what we call direct current circuits or DC circuits. And the idea of a DC circuit is that the current is constant in magnitude, except for, of course, the RC circuits, we'll see the current changing with time. But what we're really sort of contrasting it with is alternating current. The types of circuits that this would apply to would be flashlights, wiring in automobiles. Those would be direct current circuits. When we're talking about alternating current, the way the alternating current looks like is literally the current has a sinusoidal nature to it. And this is what you have when you plug something into the wall. Your household electrical power is in alternating current. Keeping in mind, something like this has a certain frequency, and what you may be aware that if you travel to another country, you need an adapter in order to plug your things into their plugs, and that's basically because in different countries they are producing alternating current at different frequencies. All right, so the first thing we're going to look at today is we have resistors in series or in parallel. And so these two pictures are showing that. This picture right here is resistors in series. Fortunately, we've already looked at series and parallel with capacitors, so we should be fairly familiar to what differentiates them from each other. Basically, resistors in series are just connected one after the other. And we'll talk about the qualities of current and potential in those situations, and then also how we can find an equivalent resistance. So that's going to be very similar to what we did with capacitors. This picture right here is resistors connected in parallel, and also we're going to investigate how we would add those resistors in parallel so that we could get an equivalent resistance, and also we are going to also understand how the potential and the current changes. You're going to see that the rules for adding resistors in series and parallel are going to be different than those for capacitors because the relationship we're using is going to be different. We're going to be focusing on Ohm's law. However, how potential depends is related in when we have resistors in series is going to be the same as what we saw for capacitors in series, same thing for parallel. And then also the rules we learned about charge for capacitors in series and parallel will be mirrored by what we see about the current in resistors in series and parallel. Okay, so if we have, these are resistors in series, And what we're going to find is that the current through all three resistors is the same because there's nowhere for the current to go. So we find that the current through resistor 1 is the same as the current through resistor 2, which is the same as the current through resistor 3. So we'll just call that current I. Now what we do find is, remembering Ohm's law, that the potential drop across each resistor will be related or will be determined by the current going through that resistor and the value of the resistance. So the potential across resistor 1 is going to be I times R1. Potential across resistor 2 is going to be I times R2. And the potential across resistor 3 is going to be I times R3. But notice that, sort of as we talked about going around a loop in a circuit in the previous chapter, the total potential from points A to B is equal to the potentials across each resistor if we added them together. So these are two important rules for resistors. Oops, I didn't really want that to be like that. Resistors in series and parallel is that the current is the same through all of them, and the sum of the potential drops is equal to the total potential across all the resistors. If we put those two things together, and so I1, if we call this the total current times the equivalent resistance and replace the I1s and I2s by just R, because they are all the same, we see that we can get rid of the current because it's the same in every term, and the equivalent resistance for resistors in parallel is just the sum of the resistors. And so that's the rule that we learn. And so notice that that's not what we found for capacitors, but that's because we were using, for capacitors, we were using Q over V, and so that different functional relationship leads to a different expression. So in addition to remembering this is how we add resistors in series, we should also remember that the potential drops adds together and the currents through each resistor are the same. Now, when we talk about resistors in parallel, remember that what we said is when you have things in parallel, there's a point where things can branch off. And here we see three different branches. The current's coming into point A, but then it has three different branches that it can go through to go through those three resistors. And it will end up coming together at point B to then travel out from that point. And so in these cases, these 3 points, these three resistors are in parallel. So the first thing that we could do is we could say, well, I'm going to label the current in each of these branches because they are definitely going to be different, because you take a current coming into a point and then that total current has to come out of point A, but it's going through different branches. So we could say that the total current is equal to the sum of those three currents. But we also learned, when we talked about capacitors in parallel, we learned that the potential drops across each of those capacitors was the same, and this is also going to be true for resistors in parallel. So the potential across resistor 1 is equal to the potential across resistor 2, which is equal to the potential across resistor 3. So those are our two rules, and we're going to use this in a combination with Ohm's law to figure out what the equivalent resistance is. This time, we're going to rearrange this and that current can be written as potential over resistance. And we're going to take this and substitute it into this expression for current. So here is where we do that. We have VAB over REQ will stand in place for the total current. And then we have V1 over R1 and V2 over R2 and V3 over R3. Now remember that I could actually rewrite this. All these are equal, so I could get rid of those, and I'm left with on over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So this rule is different from what we found with capacitors, again, just because we're using Ohm's law instead of the relationship for charge, voltage, and capacitance. But remember, some of the things that are the same is that the relationship we found for the current is the same as what we found for charge for capacitors, and the relationship for voltage is also the same. So what we find for resistors in parallel is we add the reciprocals, and that gives us the reciprocal of the equivalent resistance. My recommendation is when you're doing this math that when you can, you simply add the fractions, do a common denominator, etc. You'll be less likely to have round-off error when you do that. And also remembering that V1 is equal to V2 is equal to V3, and the total current is equal to the sum of the currents through the different branches. So these are all rules that are important for us to use. And so the basic idea is that once we go through, when we're looking at a more complicated resistor combination, we're sort of breaking them down into simpler situations using all of these rules. Okay, so I'm going to go through this to sort of help you see how we would use the rules. Now, the first thing that's really important is for me to sort of look at this circuit and understand what's happening. So I see the currents coming out of the battery and going into resistor 1, but then it hits a branch where it could go through two paths. So that means that everything here, resistor 3 and 4, actually they're in series. The fact that they're around a corner from each other isn't really important. I could put them both on the same side of that square. But resistor 3 and 4 are actually in series with resistor 2. And then we come back together at this point, and then we go into here. So then another way to think about it is resistor 1, and then this combination of resistors in parallel, those are in series, and then also in series with resistor 5. What we like to do is we need to break these down by step and simplify them. So we sort of start right here with these two that are in series. And we have to replace them by an equivalent resistor. So R equivalent here is equal to R3 plus R4 because they're in series, and so we just add them. So we get 5 plus 15 equals 20 ohms. So now we can simplify this picture. This is R1, which is 25, and then we have two in parallel with each other. One is R2, which is 60, and then the other one that we just found, this is what's standing in for the resistors in green, is 20 ohms. And then finally we come out of here, this is R5, which is 20 ohms, and then we go back into the battery, which is 120 volts, I think. Okay, so the next thing we want to do is we want to take the two that are in parallel with each other and break those down. And so we want to add those together. So 1 over equivalent is equal to 1 over 20 plus 1 over 60. And this is where I'm going to say use your fraction skills because you'll get a better answer. So this is 4 over 60, which is 1 over 15. So the equivalent here is 15 ohms. All right, so that means we can rewrite this. This is 120 volts. This is R1. This is now 15 ohms. And this one is 20. And so the total equivalent that we get here, these are all in series, at 25 plus 15 plus 20. So it's 45 and 15, that's 60 ohms. So basically what we've said is this entire circuit can be replaced by a circuit of 60 ohms. And V equals IR. This is where I would find then the current flowing through this circuit, and I'm going to start working my way backwards. So, I is V over R, so it's 120 over 60, so I got 2 amps. So, I got 2 amps running through this, and this is the same as the current that's running through here. But then I can use V equals IR to figure out the potential drop across each of these resistors. So V here is 2 amps times 20, so that's 40 volts. This one is V equals 30 volts because I'm taking 15 times 2, and then this is 50 volts. Now, let's see if this makes sense. I add 50 plus 30, that gives me 80, plus 40 is 120, which is the voltage of the battery. That makes total sense. So this is the 20 ohm resistor, and this is R5, and then this is R1. So I'm kind of done with those, but this 15 ohm resistor right here is standing in place of these two, and so I can continue to do my work to figure out currents and voltage across resistors. So notice here the 30 volts is what is across this equivalent 15 ohm resistor. So because I know that resistors in parallel have the same potential drop, that means that this resistor has a potential drop of 30 volts, and so does this one. And so that helps me figure out how much current goes through each one of those. I can use Ohm's law to do that calculation. It turns out that the current through here is 0.5 amps, and the current through this resistor is 1.5 amps. I just used I is equal to V over R. Notice that the current through these two branches adds up to be 2 amps, which was the total current through the circuit, and that makes total sense. And then finally, I can go back and figure out this 20 ohm resistor stood in place for these two in series. What I know is the same about those is they each have 1.5 amps going through them because that's how resistors act. And then I can use that to figure out the voltage drop across each one of those. And the two voltage drops that I get should equal 30 volts. So that's a really quick example of how we would use our rules. We will do an example in class, but I want you to practice trying these. So let's keep going. All right. The last thing I want to talk about for today is Kirchhoff's rules. So we just did an example where we were able to use the rules for resistors in series and parallel to simplify a circuit into one resistor and one battery. Sometimes we have situations where we have a loop that has two batteries, for example, And then you're kind of like, I don't even know what to do with this. So when you see a circuit that has maybe multiple loops that current can be flowing through, but it's not obvious that there's just simply in parallel or things in series, what we want to do is we want to look at what we call Kirchhoff's rules, which are also sometimes referred to as Kirchhoff's loop rules. So there's two main rules that we use to solve problems like this. One of them is called the junction rule. So there are points in our circuit where current can be coming together or separating it. And so that's a junction. And the idea is that there may be current coming in or coming out, and the sum of the currents coming in is equal to the sum of the currents that coming out. Or we can just say the sum of the currents coming in equals 0, and then currents that are going out are actually treated as negative. So I'm just going to call this one I3 for simplicity's sake. The way we might apply the junction rule here is I1 and I2 are coming in, and then I3 is going out, so we make that negative. Another way we could do it is we could do in equals out. You'll see that we would get exactly the same result, except that it's more written like this. I actually prefer to use current in equals current out. And so when I solve a problem or I write expressions, you'll see that that's how I'm doing it. The basic idea of the junction rule is it can be related to the analogy of a water pipe, basically saying whatever pipe water comes into a particular junction has to come out. So that's another way of looking at it. Now, another rule that we are going to talk about is called the loop rule, and it talks about potential differences as we go around a loop. And it's basically saying that, as we found in the previous chapter, potential rises and potential losses have to sort of equal each other out if you go around a loop in a circuit. That's a conservation of energy idea, that however much energy we gained through potential rises or potential gains has to be equal to the energy that we lost through potential drops. And so this is how it's sort of written, that the sum of potential rises and drops, of course rises would be positive potentials, and then drops would be negative potentials. But they have to add up to be 0 if we're going around a loop in the circuit where we begin where we end. Now, the thing that makes this a little bit more complicated is, as we're going around our circuit, we need to know how we are going to determine whether something is a potential gain or a potential loss. One of the first things that you have to do with your circuit is you do have to label all your currents. You don't need any knowledge to do this. You just kind of wing it. You determine each part of the circuit where the current would have a different value. Choose a direction, label it. Once we've done that, we can apply the loop rules. And so here are some of the rules. If we're traveling around a loop and we go through a battery in the direction that takes us from the negative terminal to the positive terminal, then that's a gain equal to whatever the potential is of the battery. However, if we go around a loop and we go through a battery from positive to negative, that's the opposite direction, then we're losing potential, and that's equal to minus the potential of the battery. Similarly, we might have talked about in the previous chapter, when we go through a resistor with the current, resistors represent a potential loss. And so this is equal to minus V, which can be written as minus the current through that resistor times its resistance. Notice that is when we're going in the current direction. However, if our loop takes us in the opposite direction to the current, then we gain potential, which is equal to the current times the resistance. And so those are our rules that we use to solve these problems. So putting it all together are the steps that we follow for using Kirchhoff's loop rules. So the first thing we want to do is we want to look at the circuit and find in different branches where the current is different. And so we would label the current in each of these branches, like I1, I2, etc. And you indicate what direction you think the current is going in. Guess what? It does not matter what direction you choose. Just choose a direction. You don't have to try to figure it out. Keep in mind that, as we found a lot of times, if you chose the wrong direction, when you solve for the current, then your answer will be negative. And that's all that happens. All right. So we do that. We're going to actually then, once we've labeled the currents, we use the junction rule to get an equation that relates the currents in the equation, like I1 plus I2 equals I3 or something like that. Then we're going to look at the circuit and we're going to identify closed loops that you can follow in the circuit. You can choose whatever you want. You get to do whatever you want. Once you've chosen a loop, you're going to write an equation that talks about the potential gains and potential losses in the loop. So you'll have like plus the EMF of the battery minus current 1 times resistor 1 and so on. Just using the rules that we just looked at in the last slide and writing expressions as we go around the loop. Usually in the problems we do, most of the time we have 3 unknowns. We have 3 different currents that we have to find. So the junction rule gives us 1 equation, and then from the loop rule we're going to need 2 more because we need as many equations as we have unknowns. That's algebra. Once we write all our equations down, then it becomes an algebra problem. So what I'm going to do is I'm going to look at one example, and I'm just going to talk about how we would get our equations, and then, but I'm not going to do the algebra for you, but it sort of shows us how we would start and set up this type of problem. Okay, so here's a loop. You see that we have 2 different batteries. One's over here and one's over here. The first thing I'm going to do is I'm going to label currents. Now, basically, I see 3 different areas where we'd have different current. We sort of have this left-hand loop where it's going to be a current, this part, and then this right-hand loop. So I'm getting rid of that because I don't like those. I don't want to keep those. So we know we have 3 different currents to label. So I'm going to label this one I1. I'm going to label this one I2. I'm going to label this one I3. Notice how quickly I did that? That means something. It means I don't care. I just choose directions. Because if I got the wrong direction, it doesn't mean I get the wrong answer. It just means I get a negative answer. So now I'm going to do a junction rule, and I'm going to think about this point right here. And I notice I have current 1 coming into there, current 3 coming in there, and current 2 coming out. So when I write the relationship between those 3 currents, it'll look like this. The currents coming in are currents 1 and currents 3, and the currents coming out is current 2. So this is my junction rule. That's one equation I can use to solve for my unknowns. Now I have to choose 2 different loops. I'm going to choose one loop here, and the idea is I'm going to start at the battery. I'm going to go all the way around here until I get back to the battery. And as I go, I'm going to figure out if I have potential gains or potential losses, and I'll write them as I should. So when I start with my loop, I'm going to start with my battery. That's E1. And I'm going from negative to positive, so that's a positive potential. Now I'm going to go through resistor 1 in the direction of current 1, so that's a potential loss. So I'm going to write minus I1 R1. Then I come down through this resistor, which, that's R2. And I'm going in direction of current 2, so that's another loss, I2 R2. And then I come around to the battery, I don't hit anything else. So that's my equation. I'm going to put in numbers here as I can, just to sort of make it clear. So I had 12 volts minus I1 times 4 minus I2 times 3 equals 0. So that becomes my second equation. And then I'm going to do another loop, and just for kicks, I'm going to go around this way because I want to sort of show going through in different directions from currents and stuff. So this is loop 1, and now I do loop 2. All right, so I'm going to start at the battery again, but notice I chose to go clockwise. So I'm going to go through that battery from positive to negative, so that's a potential loss. And then when I go through, notice current 3 is going around like this, it's counterclockwise. So when I go through resistor 3, I'm actually going against the current, so that's going to make that a potential gain. So that's I3 times R3. And then likewise, I go through resistor 2 opposite to the current, and so that's again a potential gain, and that's I2 R2. And then I come around to the battery and I end up there. So putting in numbers, I have minus 8 plus I3 times 2 plus I2 times 3 equals 0. And that becomes my third equation. So basically, what I would do is I would take these three equations, and if I solve them simultaneously doing algebra, I could find my currents in each one of the branches. And I'm not going to do that today, but that would be your next step. And that is it for today.